Hello, welcome back to me explaining different applications of calculus in STEM and engineering. Today we're going to look over the derivative and the limit definition of a derivative. And today I'm going to show you how it applies to fluid dynamics. That might sound a little bit scary, but it's actually more simple than you think, and you actually have a lot of intuition with fluid dynamics. So fluids have a property called viscosity. And the viscosity basically tells us how the fluid reacts when we apply a force to it. And this is a special type of force that we call a shear stress. Again, that might sound complicated, but you have lots of intuition about it. Imagine you yourself, you're swimming in a pool and you want to splash your friend. To do that, you have to slide your hand across the water alongside that surface. You're not pressing down on the water, you're sliding it across. So that sliding motion across the surface of the water is called a shear stress. And the way the fluid reacts to that shear stress describes its viscosity. So things with low viscosity move quite easily when we apply shear stress, while things with high viscosity require a lot more force. So you can imagine that ketchup is more viscous than water, or that maybe some type of motor oil is less viscous than water. You can think about you having to shake the honey out of some jar. That's pretty difficult because honey is very viscous. So microscopically, we get viscosity from chemistry and all the different intermolecular interactions happening, but we don't really need to care about that when we're looking at the whole fluid motion and properties. So to step back for a moment, I'm going to introduce this idea of a velocity profile, and you'll see where I'm going. So you can imagine, let's say we're at the bottom of a river, and I'm simplifying the shape of the riverbed with this very uniform, long, flat plate that we have here. And you can imagine we have some water coming in over our riverbed. And what we see is that the velocity of the water on the riverbed is actually zero. That is some theorem that we have that says at the riverbed, the velocity has to be zero. And at our maximum distance, our height, so this is the y-axis, at our y maximum, our velocity is also a maximum. So we get something that's called the velocity profile, and that just shows us what the velocity looks like with some type of geometry of a pipe or a riverbed or some type of system where fluid is moving. So you can see we get this shape at y equals 0, our velocity is a minimum. At y equals y max, our velocity is maximum. So from the shape, we can actually draw another graph that gives us a little bit more information. So this may look a little bit confusing, but I'm going to put the y position on the x-axis. But it's not going to change anything about math, just what we're naming it. And on the x-axis, the y-axis actually, we're going to put the velocity. So we recall two things. So this is 0. At y equals 0, our velocity is 0. At y equals y max, our velocity equals velocity max. Just from that principle of fluid dynamics, take it as a law that we have found that the universe follows. So we have these 2 points. So let's think, to make this very simple for us, let's just say that the velocity linearly increases as we increase our position. And looking at this graph, that might not be true, but for the sake of this video, let's just think of it like that. So from this, we can actually write a function, a formula for a function of velocity that depends on the y position. So let's say that velocity as a function of y equals what? So you may recall lines that are straight, like all lines are. You can write a slope-intercept formula for this. So if you remember, the slope is delta y over delta x, but delta y over here is delta v over d delta y. So what we get here is our slope m, and we usually use m for slope. I don't know why. But anyways, we get m and y. Just like I get y equals mx plus b, here we get v equals my plus 0 because our intercept here is 0. Okay, so why do we need this velocity formula here? It's because Newton derived something for us called Newton's law of viscosity. So it looks a little bit complicated with all these Greek letters, but it's actually simple. It says in words, the shear stress, tau, remember that force is sliding across the pool, is equal to the viscosity times the derivative of the velocity in respect to the y position. So yeah, that's a handful of words, or a mouthful, I should say. So tau is the shear stress, our force. Mu is our viscosity. And dv dy is a derivative. But of what? dv dy is the derivative of our v of y. It is v prime of y, we like to say, which equals to dv over dy. So how do we calculate that? It's actually quite easy, and I think you've seen it before. So let's look at the limit definition of a derivative. So let's say we're at some point y here, and we're at some point h here. At this point y, we get some velocity v, and at this point here, at point h, we get a velocity of y plus h, because we're just adding this to this. Now, let's write this limit definition. So the limit of h approaching 0 of v of y plus h minus v of y over h. And if you remember, this equals to v prime of y or dv dy. And that's what we're looking for here. So now let's plug in the numbers. What this really just means is that we're plugging in y plus h for v of y is m times y. And you'll see it's pretty easy. So the limit of h approaching 0, we always have to write it all out, is m times y plus h minus m times y all over h. And our h is here is because we're doing h plus y minus y, which is just h. So now let's keep on doing this and simplify it a bit. So we get my plus mh minus my over h. So you can see here, my and negative my cancel each other out here. So we get the limit of h approaching 0 of m times h over, that's an h. So because these are approaching, well, h over h is 1, we can say that the limit, we can say that v prime of y equals m, which makes sense if you know what a derivative does. It takes the line tangent to our function. And in the case of a line, it is the slope of that function. That is our m. So now we know what v prime of y is, which is dv dy. So now look, we can solve this equation. This is tau equals to m dv dy, which equals to mu times m, our slope that we got. So what I didn't tell you actually is that Newton's law of viscosity is actually a differential equation. So that might also sound complicated, but it really isn't. We're just using a derivative inside our equation here. So one thing I actually like to point out here too is if we plot out tau versus our dv dy here. So that means that, and our mu, our viscosity is constant, so it's just some value. So this is constant, and m is constant, so that means our tau is constant, just some number. And this is at the point mu times m. So what this really is saying is that no matter the amount of shear stress we apply on it, our fluid doesn't change, or it changes, the velocity profile is constant. So in other words, the properties of the fluid are not going to change due to the amount of shear stress we apply to it. Thank you for listening today, and I hope that was helpful and got you interested in fluid dynamics. That's really just a small part of what you study in fluid dynamics, and use this property to understand how they move. Yep.